What we have seen in the previous two parts concern the flow of spin and charge in metallic multilayers. In such systems, the transport is governed by the drift diffusion equation in the bulk of the metals and the Kirchhoff law at the interfaces. The transport is described in terms of electrochemical potentials and currents, which may or may not be spin dependent. In the present part, I want to deal with a completely different transport regime, where quantum tunneling rather than drift diffusion controls the flow of electrons. In this regime, the density of states at the interfaces of the tunnel barrier dominate the transport, and as a result, the tunneling magnetoresistance observed in magnetic tunnel junctions exceeds substantially the magnetoresistance obtained in metallic spin valves. In the previous lecture, we talked about the metallic spin valve and its so-called giant magnetoresistance. It turns out that the magnetoresistance ratio is actually quite small in metallic systems. Consider a typical spin valve with its two ferromagnets separated by a metallic spacer like copper or aluminum. The three layers are the active part of the spin valve. That's where the magnetoresistance comes from. If you look at a real device though, you will find that many other layers are needed. For instance, there's always an antiferromagnet that is used to pin the direction of the polarizer. You also need additional layers to ensure proper growth of the multilayer stack, to prevent atomic diffusion. You also have the leads from which the electrical current is injected, and so on. All these layers add resistances in series, which impedes the magnetoresistance by enhancing the overall resistance of the structure. So ideally, the only way to get a really large, giant magnetoresistance is to enhance the resistance of the active part. By active part, I mean the central region that includes the two ferromagnets and the spacer. This is achieved by using a tunnel barrier. To understand how spin-dependent tunneling works, we will first try to understand how to access the polarization of the density of states of a transition metal ferromagnet. So here's a typical density of states, with a strong splitting between up and down states. To probe this density of states, the idea put forward by Tedorov and Mesove in the early 70s is to use a superconducting lead. For instance, aluminum at low temperature. In the absence of an external magnetic field, the density of states of the superconducting quasiparticles looks like that. It has particle-hole symmetry and possesses a gap between the quasi-hole and the quasi-electrons, which correspond to the energy you need to break a Cooper pair. So at zero bias, there's no current flowing in the tunnel junction because the Fermi level lies in the superconducting gap. The current starts flowing only as soon as the bias voltage applied across the junction compensates the superconducting gap. This happens at positive bias, and you see that the quasi-holes can jump from the superconductor into the ferromagnetic metal. This also happens at negative bias, where the up and down electrons jump to the quasi-electron states. So this is what Tedorov and Mesove measured in the early 70s. They used nickel iron separated from an aluminum lead by a tunnel barrier made of aluminum oxide. And they indeed got two symmetric peaks of conductance at positive and negative bias. Now let's do it again, but while applying an external magnetic field. If the field is not too strong, you don't break the superconductivity and simply split the density of states of the superconductor. You see that things are becoming more interesting. If I apply a positive bias, the Fermi energy of the metal will first meet the up quasi-hole bands. And if I increase further, it will meet the down quasi-hole band. Since up and down electrons have different density of states, I shall obtain two different conductances. Symmetrically, I can apply a negative bias. The Fermi level will first meet the down quasi-electron states, and afterwards the up quasi-electron states. As a result, I will obtain 4 peaks of different magnitudes as shown in the graph. By taking the ratio between these different peaks, I can deduce the polarization of the density of states of the ferromagnet at the Fermi level. The typical polarization of a few selected transition metal ferromagnets measured by this technique are shown here. They range from about 29% for nickel iron to 48% for cobalt iron. Now let's consider a magnetic tunnel junction composed of two ferromagnets separated by a tunnel barrier. On the top panel, I represent the density of states of both ferromagnets when their magnetizations are parallel, and in the lower panel, their magnetizations are anti-parallel to each other. You immediately see that in the parallel configuration, the tunneling current is dominated by the down electrons because they possess the largest density of state at Fermi level. Now, in the case where the magnetizations are anti-parallel, the density of states on the right ferromagnets are exchanged. Now, the up electrons possess the largest density of states. So as a result, the tunnel current is equally distributed between the up and down electrons. The first experimental realization of the magnetic tunnel junction is due to Julliere in 1975. In this pioneering experiment, he used a tunnel barrier made out of germanium, and he obtained a tunneling magnetoresistance of about 15% at 4 Kelvin. In 1995, Mudera and Miyazaki made a fantastic breakthrough by using aluminum oxide as a barrier. They obtained up to 20% of tunnel magnetoresistance at room temperature. This very important result had a massive impact in the development of spintronics. First, it enabled the fabrication of highly sensitive magnetic sensors, much more efficient than metallic spin valves. Second, because the overall resistance of this tunneling device is quite high, it is compatible with semiconductor technology and can be used as a basic brick to build up hybrid spin-based devices embedded in semiconducting circuits. I gave a very qualitative explanation of the spin-dependent tunneling. Now I would like to be a bit more quantitative. I can model the tunneling process using Fermi's golden rule that states that the tunneling rate from one state to another is governed by the matrix element of the coupling term, ensuring that energy is conserved. From this rule, I can get the tunneling currents from the left to the right and from the right to the left. Here, I have the density of states of left and right electrodes, the tunneling matrix elements, and finally the Fermi-Dirac distribution that tells you that you can only jump from one state to another if your original state is occupied and your final state is free. Combining these two currents, I obtain the total current that tunnels through the junction. You see that it is proportional to the difference between the Fermi-Dirac distributions of the left and right electrodes. By assuming zero temperature, I can expand this expression to the first order in bias voltage, and I finally get the linear response of my junction. We made some pretty good progress. But now we have to handle the summation of the states K and P. To do so, we'll make another assumption. We will consider the case of a thick, high, and amorphous tunnel barrier. So I essentially drop the momentum dependence and obtain the conductance of my tunnel junction as a product of the square of the tunneling matrix element with the densities of states of the left and right electrodes. Jumping from there to the tunneling magnetoresistance is quite simple. We have spin polarized density of states on each side. So in the parallel configuration, the conductance is the sum of the product of the density of states for the same spin on each side. And in the anti-parallel configuration, this is the sum of the product of the density of states of opposite spins. This gives a formula for the magnetoresistance that can be expressed in terms of the polarization of the density of states in the left and right electrodes. Finally, I get what is known as the Julliere formula. At this stage, I'd like to make an important remark. As we have seen previously, the density of state of iron, cobalt, or nickel looks like this. So the electron whose magnetic moment is aligned on the magnetization have a small density of state. I'm going to call them the up electrons. In contrast, if the electron whose magnetic moment is anti-aligned with the magnetization have a large density of state, I'm going to call them the down electrons.
So if I inject a current in the bulk of such a ferromagnet, the down electron, which have a large density of state, will experience a lot of scattering, while the up electron, which have a small density of state, will be weakly scattered. So in other words, the conductivity will be dominated by the up electrons. In magnetic tunneling junction, though, the transport is dominated by the density of states at the interface of the barrier. So in this case, the transport is dominated by the down electron, which have a much larger density of states. So in other words, if I define the polarization as the relative difference between up and down electrons, the polarization of the conductivity in the bulk of the ferromagnet will be positive, while the polarization of the density of states will be negative.
The Julliere formula is both very simple and very powerful. By fabricating a magnetic tunneling junction and measuring its tunneling magnetoresistance, it gives a direct access to the polarization of the density of states of the ferromagnetic electrodes. It has been used to characterize the spin polarization on a wide variety of materials. In the left panel, I show the polarization measured in transition metal alloys by various authors. You see that the polarization is peaked around cobalt and seems to roughly depend on the number of valence electrons. On the right panel, I show the tunneling magnetoresistance obtained for various magnetic tunneling junctions with ferromagnetic electrodes made of the same materials. The symbols are the experimental data, and the curve is Julliere's formula. And you see that this formula is working pretty nicely. Using the Fermi-Gunnon rule to derive Julliere's formula is a bit rough, because it completely disregards the evanescent nature of the tunneling states. We can get a better understanding of the tunneling transport by considering a free electron model. This model was originally introduced by John Sonzuski in 1989. So I will replace the realistic density of states by a much simpler one, where the electrons exhibit parabolic energy dispersion. The wave functions are given here. This one describes an electron with spin sigma in the left ferromagnet. KL is the propagation wave vector normal to the interface, and kappa is the component of the wave vector that lies in the plane of the interface. The second wave function represents the electron in the tunnel barrier. This wave function is written in the WKB approximation, which applies in systems where there's a potential gradient, like in the tunnel barrier. Q is a tunneling wave vector, and you see that the electron wave function is evanescent in the barrier. The last wave function describes the electron in the right electrode. Let me also give an explicit expression of the three wave vectors in the left, right, and central layers. I can write them as a function of the exchange energy, the bias voltage across the barrier, and the barrier height U. So I can connect these wave functions and compute the conductance across the tunnel junction. I obtain this expression, where G0 is the bare conductance, and P is a polarization factor called Sonzuski's polarization. The bare conductance decreases exponentially with the barrier thickness, and most importantly, you see that Sonzuski's polarization is nothing but Julliere's polarization multiplied by a term that depends on the tunneling wave vector. We wrap up this discussion by looking at the parameter dependence of Sonzuski's polarization. Here is the plot that Sonzuski gives in his paper. The polarization is computed as a function of the ratio between the evanescent wave vector Q0 and the wave vector of the incoming up electron K up. You see that if the tunnel barrier is very high in energy, or in other words, if the insulator that composes the tunnel barrier has a very large gap, then the polarization is independent on the barrier. In the limit of very large barrier height, then spin-dependent tunneling is well described by Julliere's model. But in the intermediate range, when the barrier is not too high, the effective polarization of the tunneling electrons is reduced compared to their ideal polarization, and it can even get reversed for very low barrier height. There's another important aspect that deserves to be emphasized. If you look at the transmission of an electron through a tunnel barrier, you get this expression. The wave vectors, KL, KR, and Q, all depend on the angle of incidence of the electron on the barrier. This angle is defined in the inset, and if you compute the transmission as a function of this angle, you'll see that it is peaked around theta equals 0, which means that the transmission is dominated by electrons that impinge with normal incidence on the barrier. This is easy to understand. When an electron arrives with normal incidence on the tunnel barrier, the distance it has to tunnel through is simply the nominal thickness of the barrier. However, when it arrives at some angle, the distance it needs to tunnel through is much larger than the tunnel barrier thickness. So eventually, the barrier filters out all the electrons that are away from normal incidence. Of course, the thicker the barrier, the more efficient this filtering. To conclude this discussion on the free electron model, let me give you a couple of concrete numbers. The energy height of tunnel barriers typically lies in the range of 1 to 3 electron volt, rather on the low side for MgO and on the high side for aluminum oxide. The wave vectors for up and down electrons in the case of iron, for instance, are 1.09 and 0.42 angstrom-1, and the effective mass of the electron inside the barrier is typically around 0.4 electron mass. Tunneling magnetoresistance, also called TMR, has been realized with many different tunnel barriers, such as aluminum oxide, magnesium oxide, tantalum oxide, zirconium oxide, and so on. All these devices show common behavior. The TMR decreases upon increasing the bias voltage. It can even show a sign reversal for strong enough bias, and at low temperature, you can get this steep drop of resistance, called the zero bias anomaly. How can we understand that? To understand the drop of magnetoresistance as a function of the bias voltage, I will introduce a very important device concept, the non-local spin valve. Here is a device studied by Valenzuela and co-workers. This device is really a spin valve, with two ferromagnetic electrodes, nickel iron here and cobalt iron here. However, you see that these two electrodes are not deposited on top of each other, like in a regular spin valve, but they are rather spatially separated and connected through a non-magnetic channel, aluminum here. In this experiment, aluminum is oxidized to obtain tunnel junctions where only one electrode is ferromagnetic. On top you have nickel iron, alumina, aluminum, and on the bottom you have cobalt iron, alumina, aluminum. If you flow a current on the lower junction, it will inject a spin accumulation in the aluminum channel that will diffuse toward the top junction, where it can be detected. From the signal, Valenzuela deduced the polarization of the tunnel current. You can also do the same thing by injecting a current on the top junction and detecting the spin accumulation that is diffusing toward the bottom junction. And this is what they got. The polarization measured here strongly depends on the bias voltage polarity. For negative bias, the polarization decreases weakly with the voltage, whereas for positive bias, the polarization decreases dramatically and can even change sign, exactly what is observed experimentally with the TMR. To understand these distinct behaviors, you can consider the following diagrams. For negative voltage, spin polarized electrons flow from the ferromagnetic electrode into the non-magnetic metal. Since their polarization is given by Sonzuski's polarization at Fermi level, it only weakly depends on the bias voltage. For positive voltage, unpolarized electrons flow from the non-magnetic metal into the ferromagnet. In this case, the polarization of the states that collect these electrons dramatically depend on the energy of these incoming electrons, and therefore on the bias voltage. This experiment explains why the TMR decreases with increasing bias voltage across the magnetic tunnel junction. It's because the polarization of the density of states decreases when the energy of the incoming electron increases above the Fermi level. This is not the only mechanism that contributes to the reduction of the TMR as a function of the bias voltage. Imagine that you inject electrons from left to right. In the present configuration, the conduction is dominated by up electrons, but it doesn't really matter. Now, these electrons are hot, meaning that their energy is above the Fermi level of the right electrodes. So one way they can relax their energy is by emitting a phonon. This emission conserves the spin, but it opens a channel that facilitates electron tunneling. Therefore, the overall conductance increases and the TMR decreases. Now, because these electrodes are magnetic, the electrons can also relax their energy by emitting a magnon. This mechanism works better in the anti-parallel configuration. Take an up electron from the left electrode tunneling to the right electrode. In the right electrodes, its density of state is small, so a priori, the tunneling probability is not very high. However, remember that the spin of this electron points against the direction of the magnetization, so the electron can emit a magnon by flipping its spin. The spin flip transfers this originally up electron toward the large density of states of the down electrons. This mechanism opens a new channel that is dramatically efficient and reduces the TMR substantially. The spin flip mechanism was proposed to be responsible for the linear decrease of the tunnel resistance observed experimentally. Further studies have shown that the electron-phonon and electron-magnon interactions leave a signature in the derivative of the tunnel conductance. In this picture, the peaks denoted M are attributed to magnon emission, while the peaks denoted P are attributed to phonon emission. And you see that the magnon emission is definitely stronger in the anti-parallel configuration, as indicated on the blue curve. To conclude this presentation on spin-dependent tunneling, I'd like to introduce to you the megastar material of magnetic tunnel junction, Iron-MgO. The tunneling magnetoresistance observed in this heterostructure has beaten all previous records obtained on alternative systems. It has been so influential that today, all industry majors working on magnetic random access memories are focusing on this material. So why should we expect spectacular TMR in Iron-MgO? First, let's look at the crystal structure. Both Iron and MgO are BCC crystals, and they possess very similar lattice parameter. So in principle, they could grow very well on top of each other. And most importantly, their block state should adopt exactly the same symmetries. This latter remark was pointed out by Bill Butler and co-workers in their influential paper of 2001. Second observation. Let's have a look at the band structure of iron. As I mentioned in the previous lecture, the electronic bands can be classified with respect to the symmetry of their wave function. In the case of iron, you have the so-called delta 1 bands, the delta 2 prime, delta 5, and delta 2 bands. The delta 1 states have a mostly spherical symmetry. Delta 2 and delta 2 prime possess both dx square minus y square and dxy orbital character, and delta 5 is a mixture of p and d orbitals. Now look at the spin character. Here I represent up electrons with a light color and down electrons with dark color. Well, what is truly remarkable is that iron is like a half metal for the delta 1 symmetry. You see that the up electron band crosses the Fermi level, whereas the down electron band remains above the Fermi level. In other words, the polarization of the delta 1 band is close to 100% at Fermi level. The last remarkable feature of this system pertains to the complex band structure of MgO. What do I mean by complex band structure? You know that in crystals, electrons are represented by block states, indexed by their propagating wave vector k. The band structures of such crystals are the energy bands on which this wave vector is real, so that the electron can propagate. You could extend this concept to evanescent states. For instance, let's take a particular block state of iron. This state is indexed by a real vector k and a band indexed n. In the gap region of MgO, one can define a block state associated to the same band n, but with a complex wave vector that describes its evanescent propagation. Here you have this complex band structure computed by Dederish and Mavropoulos. Note that not all the bands are represented. but you have at least the delta 1 in red and delta 2 prime delta 5 in green. The central panel showed the real band structure with the gap marked here. And on the left and right panels, you have the imaginary band structure for two different real parts of the wave vector. What you see is that in the gap, the evanescent wave vector of the delta 1 states is much smaller than the evanescent wave vector of the delta 2 prime delta 5. Which means that the delta 1 states can tunnel very efficiently, while delta 2 prime delta 5 and even delta 2 states are strongly damped. In other words, MgO acts like a symmetry filter for delta 1 states. So in summary, we have two materials with the same crystal symmetries and an excellent lattice match. In addition, iron is a half metal for delta 1 states, and MgO massively favors the tunneling of these states. We have everything we need to get a large TMR. Let me show you how these features reflect in the actual calculation of the tunneling transport. These figures have been computed by Butler and coworkers and represent the tunneling density of states across an Iron-MgO iron junction for the different block states. We start with the parallel configuration. The left panel is for up electrons and the right panel is for down electrons. You immediately see that the delta 1 states dominate the conduction for up electron, while they are completely absent for the down electrons. The other states, delta 2 prime and delta 5, are also present, but they are massively evanescent in the MgO layer. Let's consider the anti-parallel configuration. Again, up electrons are dominated by the delta 1 character, while this character is absent for down electrons. But take a closer look to the up electron panel. You see that the tunneling density of state carries on decreasing linearly in the right iron electrode. This means that they are evanescent, even after passing the MgO layer. This completely makes sense, because iron is a half metal for delta 1, so in the anti-parallel configuration, the right layer acts like an additional tunnel barrier for the delta 1 up electrons. Iron-MgO junctions have been grown successfully about 15 years ago by Parkin's group in the US and Yuasa's group in Japan. They immediately obtained very large TMR, around 200%, much larger than the one obtained with aluminum oxide. You can notice that the MgO barrier is crystalline, contrary to aluminum oxide that is amorphous. The crystallinity of the MgO barrier ensures very high quality growth that can lead to coherent tunneling behavior. This is what you see in this picture, where the TMR is reported as a function of the barrier thickness. These nice oscillations can be related to the interference pattern between bulk states and interfacial resonance states. These resonance states are particularly important when reducing the barrier thickness and substantially reduce the overall TMR. There's a lot more to say about these junctions, and in particular about these interfacial resonance states, so I encourage you to have a look at these reviews. Magnetic tunnel junctions are really central to the development of applied spintronics, so I'd like to spend a slide to quickly discuss the stakes and challenges of device fabrication. So what are the performance criteria? A large GMR to get a large signal, a small or tunable resistance area product to ensure that the junction can sustain large current densities, optimal magnetic properties, and of course large reproducibility and so on. What are the challenges? The material's growth comes first. Growing a metallic thin film on top of an oxide is difficult because the metal tends to form small clusters, which leads to irregular interfaces. You want to ensure the materials are properly textured, roughness is reduced as much as possible. You also want a good barrier quality, well oxidized, free of pinholes and defects. And finally, you want to control the atomic diffusion across the stack. You want to make sure that when you deposit a ruthenium layer, these ruthenium atoms will not diffuse to the other end of the device. The first thing you can do to improve the barrier quality is to anneal the sample. As a matter of fact, when you oxidize a metal, or when you deposit a metal oxide, there's always a bit of oxygen atom that diffuse toward the neighboring layers. By heating the sample, you bring vibrational energy to these atoms, and in particular to the light ones like oxygen. This way, the oxygen atoms minimize their energy by going back to the barrier. In other words, you improve the quality of the barrier by improving its oxidation. Here, Souza and co-workers annealed an aluminum oxide barrier and obtained a dramatic improvement of the TMR around 230 degrees Celsius. This improvement is correlated with an optimal barrier height and an optimal barrier thickness, which are associated with an optimal oxidation condition of the barrier. Now, increasing the annealing further favors the diffusion of certain chemical species, such as manganese, ruthenium, boron, that can deteriorate the performance of the device. So you have to fine-tune and find the best annealing conditions. In the case of Iron-MgO, the objective is to obtain a nicely crystalline tunneling barrier. To do so, experts use amorphous cobalt-iron-boron magnetic electrodes and anneal up to 400 degrees Celsius. You see that at 250 degrees, the interfaces are improved, which means that the oxygen that had diffused into the ferromagnetic electrodes are now back in the MgO. And around 375 degrees, even the cobalt-iron-boron electrode starts crystallizing. The job of device engineers is really about finding the proper recipe to reach a compromise between high TMR and low resistance area product. And this comes out of long systematic studies that involve the deposition conditions, choice of materials, and so on. Since the discovery of the German magnetoresistance in 1988, immense progress has been achieved. In the decade that followed Fert's and Grunberg's experiment, it has been quickly realized that metallic spin valves could never yield more than a few percent at room temperature. This is why the effort has been focused on magnetic tunnel junctions. As I mentioned previously, the superiority of tunnel junctions comes from the fact that the resistance of the tunnel barrier, which constitutes the active part of the device, dominates over the resistance of the metallic layers composing the stack. Therefore, you can put virtually as many additional layers as you want, the TMR remains dominated by the barrier. From this standpoint, aluminum oxide has gathered a lot of hope for about a decade, but its TMR quickly saturated around 70%. The discovery of Iron-MgO systems has been a revolution and is now dominating the market. To the best of my knowledge, the TMR of MgO-based junctions has saturated about 10 years ago around 400% at room temperature and around 1000% at low temperature.
In this lecture, we have seen how charge and spin travel through metallic multilayers and tunnel junctions. In metallic multilayers, the transport is governed by spin accumulation and spin current that give rise to magnetoresistive effects. In magnetic tunnel junction, the transport is controlled by quantum tunneling and the interfacial density of states. As such, the tunneling magnetoresistance can be orders of magnitude larger than the magnetoresistance of metallic devices, because the overall resistance of the magnetic device is controlled by the spin-dependent tunneling. So in a nutshell, this lecture was about the influence of the magnetic configuration on the spin transport. In the next lecture, I want to take the opposite perspective and look at the influence of the spin transport on the magnetization direction. What we are going to see is that through transferring the angular momentum from the spin current to the magnetization, one can induce a magnetic torque that enables the electrical control of the magnetization direction.